Okay, so yeah, so hello all. I'm Catherine Sanchna, a PhD scholar from IIT Madras. I'm one of the TAs for this course, Mechanical Characterization of Bituminous Materials. So in this tutorial session, which happens every Tuesday between 6 p.m. and 8 p.m., we will be discussing previous year's assignment questions and their solutions. Okay. And this video will be recorded and posted on my YouTube channel. The link for which will be can be found in the NPTEL website. And also, if you have any questions regarding with respect to the questions that we are seeing now, you can either comment below my YouTube video or post it in the discussion forum of the NPTEL website. So without any further delay, we will begin this session. So here we are stepping into the 7th week, okay, and in this week the following are the lectures that have been covered. Okay. So yeah, 4 lectures on PG grading, on PG grading or performance grading of bitumen, okay, and one on modified bitumen. Okay. So in this 4 lectures, first one is the continuation of PG grading. Okay. Then the theoretical background to this PG grading, okay, the criteria, how the parameter for the PG grading has been derived, okay, the theoretical background. Then one lecture on low temperature grading, PG grading, and one on continuous grading. Okay. So we will be going through the questions in the following manner. So if we see any questions on modified bitumen, we will skip them and see them at the end. And any questions on any of these PG grading, we will be solving them first. So we will begin with the first question. The flexural modulus of a prismatic beam of constant cross section loaded at its midspan. So first we need to understand from where this question has been asked. So out of these 4 lectures, okay, out of these 4 topics, under which topic does this question come under? Okay, so this is for a prismatic beam. Now you know that for PG grading of bitumen, the following samples are used. Okay, so PG grading you have 3 distresses, right? One is rutting, fatigue, and low temperature cracking. Right? And for these, you will be testing using a dynamic shear rheometer, for which the sample is a cylindrical sample of diameter 25 mm and height 1 mm for rutting, and diameter 8 mm and height 2 mm for fatigue. So here the sample is cylindrical. So this question does not pertain to rutting or fatigue where the sample is tested in a dynamic shear rheometer. So it pertains to low temperature cracking, where we use a bending beam rheometer. So as the name says, you can see that it is the test is carried out on a beam of bitumen, okay, a small beam of bitumen. Now efforts have been made to um, determine the low temperature grade of bitumen by using a dynamic shear rheometer also, okay, by either using a 4 dia and height of 1.5 or something, or height 3 like that, okay. So there are many studies that are evolving, okay, to use a dynamic shear rheometer itself to find out the low temperature um, grade of bitumen, but it is yet to be implemented in ASTM, or we do not know when this implementation will be made, okay. And also there are efforts have been made to determine the low temperature cracking grade by using a bending beam rheometer in a DSR, okay. So not bending beam rheometer, okay, so it a bending beam in a DSR, okay. So that is also evolving, but now for that we will see uh, for now we will just see bending beam rheometer, okay. And what is the criteria or how it has been developed, okay. So now, as the name says, it is a beam, a prismatic beam. So it is a prismatic beam, okay. And if you see this beam sorry, this beam is simply supported at its ends, okay. So we all have some basic knowledge on strength of materials, right? So we know what a simply supported beam is. The beam is simply resting on two supports, okay. It does not have any restraints, and there is a load, a concentric point load in the center, applied in the center of the beam, okay. And you know how this load is applied? It is applied like this, like a constant load with time, okay. So this load P is being applied on the beam. So for now we will ignore the influence of time and see how this beam is going to deflect, okay. Okay, so let us take a simply supported beam with a point load at the center. You know the shear force diagram, right? It will be like this, okay. So to know the shear force diagram, you have to know the support reactions, right? So the support reactions is, you know, summation of vertical forces is 0. So the support reactions are P by 2 and P by 2, because the load is applied exactly at the center, right? So now this is the shear force diagram. And how will a bending moment diagram look? It will be like this, with maximum bending moment at the center, okay, and 0 at the ends. Why the bending moment is 0 at the ends? Because there is no restraint, so the beam is free to deflect at the ends. There is no restriction on the ends. So only if there is a restriction, when the beam is trying to bend, there will a moment will be generated, right? So here it is free to deflect at the ends, and so the bending moment at the ends is 0 and is maximum at the center with a value of PL by 4. So you should be knowing how this value is obtained, right? So if you you draw, if you take a cross section and if you take the bending moment is P by 2 into L by 2. So that is how you will get the maximum bending moment. Now, if you want to know the deflection of the beam, okay, so from the deflection equation for the beam, okay, you know that this is the equation. From this only we can derive shear force and from this we can determine the deflection of the beam. How you can do this? So if you take integral of this twice, a double integral, you will end up with a function of x, okay, a deflection as a function of x. So you will get the deflection across the beam, okay. Now you know what m is, right? So you have to take m at a section x, okay. Find m at a section x, then you integrate it twice, okay. So you will integrate, if you integrate it once, you will get dy by dx, and you integrated it one more time. So here you will have one equation plus a constant, and you integrated it one more time, you will get one more equation, one term plus one more constant, right? And to get these constants, you have to substitute the boundary conditions. And what are the boundary conditions for this deflection? So at x is equals to 0, which is this point, the deflection is 0, right? And at x is equals to L, which is the length of the beam, again the deflection is 0. So x is equals to 0, y is equals to 0, and x is equals to L, y is equals to 0. So by substituting these two conditions, you can get the constants C1 and C2. And now you will know so when you substitute for C1 and C2, you will get y as a function of x. Now you want to know the maximum value of y, or the maximum deflection of the beam. You know that the maximum deflection will occur at the center, okay. And so in this you have to substitute, instead of x you have to substitute for L by 2 to get the maximum deflection. So that deflection, if you see, will be equal to PL cube by 48 EI. So this is the maximum deflection of the beam. Now they are asking you to find out the so now they are asking you to find out the flexural modulus of the beam, okay. So what is this EI? E is the modulus, flexural modulus, okay, because the beam is subjected to flexure, and I is the moment of inertia. Okay. So if you want to find out the flexural modulus, just take e to the other side. So e is equals to PLQ by 48 into deflection max into I. Now if you see any of these options, you will never see the term I, which means the value of I has been substituted, okay, for in this equation. What is the value of I? What is the moment of inertia? For a rectangular beam, okay, of breadth B and height h, This is the moment of inertia. Okay, so now when you substitute for the moment of inertia, you will get 48 delta B h cube into 12, which is nothing but PL cube by 4, okay, delta BH cube. This is your equation for flexural modulus. So the answer is PL cube by 4B delta H cube. Okay. Now moving to the next question. So what we saw is something corresponding to a bending beam rheometer. Now I did not tell you how this E and deflection are related to the beam. So when you now in the case of a bending beam rheometer, you will subject this beam to a constant load with time. Okay. Now you know that our beam is a viscoelastic material. So the deflection of the beam will also be a function of time, unlike the deflection of the beam will also be a function of time. Okay, and from this deflection only you can get the stiffness of the beam, okay, as a function of time. So using this value, okay, you will be able to find out the PG grade of bitumen, low temperature PG grade of bitumen. Okay. So now, so how is this related? You will apply a constant load, measure the deflection of the beam at the center, which varies as a function of time. So this equation that we saw is for an elastic beam. For a viscoelastic material, they have simply substituted delta, okay, which is a constant value in the case of an elastic beam, to be a function of time. So you substitute a function there, and the stiffness of the beam, which is supposed to be constant for an elastic beam, okay, is also substituted as a function. It is a function of time. Since delta varies with function, E also varies with function. Okay, the modulus also varies with function. Now this modulus, okay, is plotted as a function of time, and based on the parameters, okay, obtained from this curve, okay, E versus T curve, the PG grade of bitumen at low temperature is determined. Okay. Now moving to the next question. If the G star into sine delta, okay, is 21.5 degrees Celsius, maximum 5000 kPa criteria, I'm going to change this to 6000 now. Okay, I will tell you why. The likely intermediate PG temperature is what? So now we will move to the next question, okay, which is related to the intermediate PG temperature. So first let us understand which distress this corresponds to. This corresponds to fatigue cracking. So you know that fatigue cracking occurs at intermediate temperatures, rutting occurs at high temperatures, and low temperature cracking occurs at very low temperatures, right? So now what is the criteria for this fatigue cracking? Okay, so now you are going to test the bitumen in a DSR, dynamic shear rheometer. So the dimensions of the sample we saw 8 mm dia and 2 mm height. Okay, you are going to subject the sample to some intermediate temperatures and measure the value of G star into sine delta. Okay, now based on the earlier lectures and earlier tutorial sessions, you should be knowing that the fatigue cracking occurs because the material is very stiff. So in order to limit or yeah, in order to limit the fatigue cracking, your material has to be sufficiently soft. Okay, so if the material is stiff, it is prone to cracking. So you are going to limit the stiffness of the material in order to in order for the fatigue, in order to prevent or limit the fatigue cracking. So in that case, you are limiting the value of G star by sine delta to 6000 kPa. So it has to be a maximum of 6000 kPa. What do you, there are two things that needs to be noticed here. In all the lectures mentioned by sir, he would have spoken about 5000 kPa, and here I'm telling you that the maximum allowable value is of G star into sine delta is 6000 kPa, because the ASTM code has been recently revised, okay, in 2023, and they have changed the value from 5000 kPa to 6000 kPa. So now all the lectures in this NPTEL would have probably been taken 2 to 3 years back, and at that time the value was 5000 MPa. So all the lectures have this value of 5000 not MPa, sorry, kPa. And in this very recently, which is last year, they have revised the ASTM code to 6000 kPa. Okay, so how was this evolved? So initially the value was 3 kPa, and from 3 kPa they changed it to 5 kPa, and from 5 kPa they have changed it to 6 kPa now. Now this maximum this value of 6 kPa is the maximum value that the bitumen should have at that intermediate temperature to prevent or limit fatigue cracking. Okay. So what does this question mean? Now I'm testing bitumen. So when you give a PG grade for bitumen, okay, you will give something like this. You will not give the grade of bitumen as say 21.5 or 20.5 or even 20. Okay, you will not give a grade of bitumen like this. This you will call it as continuous grading, which we will see later. But if you are going to if you have been asked to give the PG grading, you have to give a particular number, okay, which is not any of this. Okay, so if you see, the intermediate grade of PG grade of bitumen should be any of these following numbers, any of these temperatures. Now if you see, these values are at intervals of 3. So these are also temperatures are at intervals of 3. If your value of if the temperature at which the maximum value of G star into sine delta 6000 kPa falls anywhere in between, okay, you have to pick, you should not take that value, but you have to pick either one of these values, because that is the PG grade. Okay, if you give the exact value, it means that you are giving the continuous grading of bitumen, okay, which you will call it as pass fail temperature according to the dynamic shearometer. Okay, the results that you get from the dynamic shearometer, you will get something called as the pass fail temperature, which is the continuous grading. But if you have to give the PG grading of bitumen, it should be one amongst these numbers, and this variation amongst the numbers, okay, amongst these temperatures is 3 in the case of fatigue and 6 in the case of rutting and or high temperature and low temperature crack. Okay, high temperature grade and low temperature grade. Now what the question says is, this is 21.5. okay, my bitumen has a value of exactly 6000 kPa at a temperature of 21.5. And now what will you give the PG grade of bitumen? So if someone asks you like this, you should say, you should always be on the safer side, right? So let us take two cases, okay. In the first case, I'm going to say that my PG grade is 19, and in the second case, I'm going to say that my PG grade is 27. Let us analyze each of these situations. So if I say that my PG grade of the binder is 19, I'm giving this binder to a contractor and I'm saying that the PG grade of this binder is 19, and let us say he's not going to verify it, he's simply going to believe you, and he's going to use this at a temperature at a place where the temperature is say 20 degrees Celsius. Now what will happen? Your binder has a maximum value of 6000 kPa at 21.5 degrees Celsius. As the temperature decreases, the stiffness will increase, right? So at 20 degrees Celsius, its stiffness will be more than 6000 kPa, which means it will fail by fatigue cracking as per the PG criteria. So if you give 19, what will happen? Your bitumen is going to fail by fatigue cracking because your pass fail temperature is 21.5. So the grade of bitumen is cannot obviously be 19. You always have to be on the safer side, right? So let us say now I'm going to tell the contractor that my PG grade of this binder is 22, and let us say he's going to use this in a place where the temperature is 22 degrees Celsius. It is good, right? It is better because at 22 degrees Celsius the binder will be a bit softer when compared to 21.5 degrees Celsius, and therefore the stiffness will be less than 6000 kPa, and so no issues, right? So he's obviously not going to use it in a place where the temperature is below 22 degrees Celsius. So you are always on the safer side. So in the case of intermediate PG grading, you always have to pick the next highest temperature. So if my PG grading is 21.5, if my pass fail temperature is 21.5, I have to pick the next highest PG temperature. What are the PG temperatures of this intermediate grade? It is 16, 19, 22, 25, 28 and so on. So what is the next highest PG temperature? It is 22. So in the case of intermediate PG grading, I have to pick the next highest PG temperature after the pass fail temperature. Okay, so this is in the case of intermediate PG grading. So first let us answer this question. So the answer to this is 22 degrees Celsius, which we saw now. Now as we are on this page, we will discuss how the high temperature grade is also determined. Okay, so the same scenario we will apply to a high temperature grading of bitumen. Okay, so the same scenario we will apply to high temperature grading of bitumen. I'm going to give you a similar example. Let us say my G star by sine delta has a maximum of, let us say this is a RTFO aged sample. We will see two cases. Okay, first let us take an unaged sample. So in the case of in order to find out the high temperature PG, you will test the bitumen in a dynamic shear rheometer with sample dimensions of 25 mm dia and 1 mm height, 1 mm height, right? And you will be subjecting the bitumen to a few high temperatures, okay, and you will be finding out the PG high temperature of the bitumen. Okay, now you will do this on two types of samples. One is an unaged sample and one is an RTFO aged sample. Okay. Now let us say that first let us see the case of unaged sample. Okay, my value of G star by sine delta, what is the limiting criteria? It should be minimum of 1 kPa. Okay, to resist rutting. Now why this minimum criteria is given? Because you know that at high temperatures the bitumen is very soft and so it is prone to rutting, prone more to rutting. Now in order to resist this rutting, the bitumen has to be stiffer, right? So it should have a minimum stiffness. It should be stiff enough to resist rutting. So it should have at least this much of stiffness for this rutting, to resist rutting. Okay, so that is why we give a minimum value for high temperatures and a maximum value at intermediate temperatures, because at intermediate temperatures we want it to be sufficiently soft. So it should have, you should say that maximum it should have this much stiffness. If it goes beyond this, if it is more stiff, then my bitumen is going to fail by fatigue. So at high temperatures it should have at least this much of stiffness. If it does not have even this much of stiffness, it means that my bitumen is very soft, that it will undergo rutting. Okay, so for our next sample, say this is my criteria, and let us say for I'm finding out this criteria is satisfied when the bitumen is when the temperature of bitumen is say 62.5 degrees Celsius. Okay, so now how will you find out the PG grading of bitumen, high temperature grade of bitumen? So again, this is the pass fail sorry, where is, just a second. Yeah, so this is my pass fail temperature or continuous grade of bitumen. Okay, so it is the exact pass fail temperature. Now how will I give the PG grading of bitumen? So as I said, for intermediate PG grade, you have certain temperatures which you can call it as PG grade of bitumen, right? Which are at intervals of 3 degrees Celsius. Here also you will have a few temperatures which you can call it as the high temperature PG grade of bitumen, and they should be at intervals of, and they will be at intervals of 6 degrees Celsius. So let us say, so it is like this: 64, 70, 76, 82, like that. Okay. Now where does this pass fail temperature fall? It is in this region. Okay, 62.5. Now there are two cases. Like, now how will I give, so this is the exact pass fail temperature. Now I have to determine the PG temperature. What did we do for intermediate temperature? We said that the PG intermediate temperature is the next highest PG temperature after the pass fail temperature. Let us see if the same thing holds for a high temperature grade. Okay, 62.5. So what could be the possible PG grading of bitumen? There are two cases. Either it is 58 degrees Celsius or 64 degrees Celsius. This is my PG grade. Now let us check with 64 degrees Celsius, because this is the criteria that we gave for intermediate PG grade. Okay, what we said, it should be the next highest temperature after the pass fail temperature. So let us first check if this works for high temperature. Okay, now I'm going to give this grade of give the PG grade for this bitumen as PG 64, and I'm going to give this to a contractor. He's not going to check it, and he's going to believe you, and he's going to use it. Now let us say he thinks that the maximum temperature to which the bitumen can be subjected to is 64 degrees Celsius, and so he's going to use it in a place where the pavement temperature is 63 degrees Celsius. Okay, so now what will happen? Your pass fail temperature is only 62.5 degrees Celsius. As temperature increases, right, your bitumen will become even more softer, right? So the G star by sine delta value will become less than 1 kPa. and if it becomes less than 1 kPa, what will happen? It is prone to rutting, because the criteria is it has to have a minimum stiffness of 1 kPa. So now it will fail by rutting if you pick the next highest temperature, right? So this cannot happen. Let us check with 58 degrees Celsius. So I am going to say that my PG is PG 58. Now my contractor, I gave it to my contractor. Though my high temperature, pass fail temperature is 62.5, he does not know that, right? He thinks that the highest temperature to which the bitumen can be subjected to is 58 degrees Celsius. And so he's going to, let us say he's going to lay it in a place where the high temperature is say 58 degrees Celsius. Okay, exactly 58 degrees Celsius. What will happen? As the temperature decreases, the G star by sin delta value will increase, right? And so it will have a value more than 1 kPa. And what will happen when it has more than 1 kPa? It has sufficient stiffness to resist rutting. So this is better, right? So we should always be on the safer side. So what did we see for intermediate? So it is like this, okay? High temperature, intermediate temperature, so if this is my pass fail temperature, so if this is my pass fail temperature for high temperature, okay, this value, and this is my pass fail temperature for intermediate temperature, I should always pick PG temperature as the next highest temperature for intermediate PG temperature and next lowest temperature for high temperature PG grade. Okay, so it is like this, it is on either sides. Okay, so this is how you will determine the PG high temperature and intermediate temperature of the bitumen. Now what we saw is for unaged bitumen, right? For high temperature, what we saw is for unaged bitumen. Similarly, for RTFO aged bitumen, the same story, but instead of 1 kPa, it is going to be 2.2 kPa. Now, both unaged and RTFO aged is for high temperature grade, right? Let us say when I tested unaged bitumen, okay, I got the PG grade. Now you know how to determine the PG grade of bitumen, right? Let us say my PG grade itself is changing, okay, by 1. Let us say my PG grade is 64, and when I did RTFO, my PG grade was found to be 70. Okay, it can happen. Okay, it can either be more or less. Okay, anything can happen. So now you have 2 PG grades, okay, for the same bitumen at 2 aging conditions, but you have to give only one high temperature PG grade of bitumen. So how will you do? As I said, you should always be on the safer side. So what now again we will take 2 cases. What will happen if I give the PG grade of bitumen as 64 degrees Celsius? It means that my contractor will think that the maximum temperature to which the bitumen can be subjected to is 64 degrees Celsius, and he will use it in places with temperatures less than 64 degrees Celsius, which is better because it will not be prone to rutting. Now if he uses at 70 degrees Celsius, there are chances that the bitumen is prone to rutting. So in order to be on the safer side, you should always pick the lowest value. So for high temperature, we always pick the lowest value, right? So here we pick the PG grade of bitumen to be 64 degrees Celsius, PG 64. Okay, so this is for high temperature PG. Now in both intermediate and high temperature, what we saw is we were given, just a second, okay, we were given So we were given the bitumen and we were asked to select the grade. Okay, so you were given the bitumen, you tested it at different temperatures, and you were able to give the grade of bitumen. That's what we saw now. Now let us take the other way around. We will go the other way around. So so in this case, you are the person in the lab who is in charge of grading the bitumen which is given to you. Now let us go the other way around and say that you are the contractor and you've been asked to lay the road in a particular place. So now you have to ask for a particular grade of bitumen, right? So how will you do that? Now you have to, so what we saw, you have to do the exact opposite of what we saw. So what will happen is, so you will first go and measure the high temperature of the place. Okay, maybe it is air temperature or pavement temperature. Okay, so you will measure the air temperature and convert it into pavement temperature, okay, by using some empirical relations, or you can directly get the pavement temperature if you have the necessary data. Okay, now after getting the pavement temperature, you will do some reliability adjustments. So sir would have explained what this reliability adjustment is. So if my PG grade is, say, pavement high temperature is, say, 58 degrees Celsius, I will not say that my pavement temperature is 50 degrees Celsius. I will go a little on the higher side in order to account for the variability that is expected in the field. Okay, so there is variability expected in the field, right? So there, in order to account for that, instead of saying that my PG is 58 degrees Celsius, if I want a 98% reliability, let us say, when I give a 98% reliability, let us say my value is 60 degrees Celsius. Okay, now I know that my the pavement temperature is 60 degrees Celsius. Now what grade of bitumen will I ask for? Okay, here also PG grade, there are only these specific temperatures which you can call it as grade. As I said earlier, 58, 64, 70, 76, 82. So okay, it is like this. Now you have to ask, so it is at intervals of 6, right? So now you have to ask for this grade of bitumen. You want a particular grade of bitumen. Now where does this 60 fall? It falls in between 58 and 64. So when we graded a bitumen, what did we do? We picked the PG grade of bitumen as the temperature, as the next lower temperature below the pass-fail temperature. So if this is my pass-fail temperature, I would have picked my PG grade of bitumen as 58. Now you are going the other way around. You are asking for a particular grade of bitumen which can be used for a place where the maximum temperature is 60 degrees Celsius. So now it can be either 58 or 64, right? It cannot be, it can be other temperatures also, but the closest value we have to pick, right? So it can be either 58 or 64 degrees Celsius. And my 60 is going to fall in between. Now let us take two cases here again. So what did we say for PG grade of bitumen in the lab? So it has to be the next lowest temperature after the pass-fail temperature. So let us first check for 58 degrees Celsius. Now my pavement is subjected to 60 degrees Celsius. Okay, and if I am going to ask for a bitumen whose PG grade is 58 degrees Celsius, what will happen? Beyond 58 degrees Celsius, it cannot, it will become softer, right? So if my temperature goes beyond 58 degrees Celsius, temperature of the place goes beyond 58 degrees Celsius, because it is expected to go, right? Because what I am giving is 60 degrees Celsius, but you are going to give me a bitumen which can go only up to 58 degrees Celsius without rutting. So I should not ask for a PG grade of 58 degrees Celsius, I should ask for a PG grade of 64. Only then, if I get a PG of PG bitumen whose PG grade is 64, then I can use it in a place whose maximum temperature is 60 degrees Celsius. So even if my temperature goes to 61 or 63, it is not going to be a problem. I'm saying that until 60, this PG grade of 64 can satisfy my requirements. Okay. So when you are in the lab and you are asked to grade the bitumen, you will do it one way, and you will do it exactly the opposite way when you are in the field and you are asking for a grade of bitumen. Okay, so when you ask for a grade of bitumen whose maximum temperature is 60 degrees Celsius, you will ask for a PG grade of 64. Okay, to be on the safer side. Similarly, for intermediate temperature. Okay. So now let us say my intermediate temperature of the place is 20 degrees Celsius. Now what are the PG intermediate grades? 19, 22, 25, 28 and so on. So now it is going to fall between 19 and 22. What did we say for the PG grade of bitumen? So if my pass-fail temperature is 22, I will pick the next highest temperature after the pass-fail temperature as the PG grade of bitumen. Now I am in the field and I am saying that my intermediate temperature of the place is 20 degrees Celsius. So if I take 22 as my if I'm going to request for a bitumen whose PG grade is 22, what will happen? In my field, my temperatures can go below 22 also, up to 20, and so the bitumen cannot satisfy my requirements. Okay, so till 22 the maximum criteria of 6000 kPa is reached. Now when I go below 22, the stiffness of the bitumen will be even more higher, and so my bitumen cannot satisfy the fatigue criteria requirement. Now if I ask for a PG grade of bitumen, a bitumen with a PG grade of 19, so my bitumen can survive in conditions up to 19 degrees Celsius, and the lowest intermediate temperature that my pavement will be subjected to is only 20 degrees Celsius. So I have this liberty of going till 19 if I pick a PG grade of 19. So it is the other way around in the field. So if I'm in a place whose intermediate temperature is 20 degrees Celsius, I'm going to pick the next lowest temperature after the pass-fail temperature as the PG grade required for that place. Okay, so this is how it is done. Okay, now moving to the next question. Addition of all this is with respect to modifiers. We'll come to this at the end. Okay. So the PG gradations are based on maximum design air temperature. Okay, so now you have two values, right? So when you say PG, you will express it as like this. So this is my high temperature and this is my low temperature. Okay, minus something is my low temperature, and you will give something in bracket which is your intermediate temperature. So this is for low temperature cracking, this is for rutting, and this is for fatigue. Okay, now you can never find out the intermediate temperature of the place. How will you find out the intermediate temperature of the place? When will you go and measure? If you know the high temperature of the place, you can easily know the high temperature of the place, right? So the highest temperature is my high temperature and the lowest temperature is my low temperature. That is as easy as that. But there are ways, so it is not exactly the exact value of high temperature. You will take a 7-day maximum pavement design temperature. So you will take a 7-day maximum. Average of the 7 days is your high temperature. Okay. Intermediate low temperature is the 1 day minimum low temperature. So for high temperature you will be averaging it out for 7 days, and for low temperature you will be taking one exact value at which the pavement temperature is the lowest. That can be easily found out, right, by measuring, or by knowing the air temperature or the pavement temperature. You can easily say that this is my high temperature of the place, this is my low temperature of the place. That is what you can measure. You can never measure the intermediate temperature of the place, right? Why? Because what is your intermediate temperature? How will you find out your intermediate temperatures? There will be a lot of temperatures between high and low temperatures which you can say that are in the intermediate regime, right? But what exactly is the intermediate temperature, we will see that later. But for now we will simply see the PG gradations. What are the actual values you can measure? So as I said, now is it the maximum design air temperature and minimum pavement design temperature? No. Okay, because it has to be, as I said earlier, for high temperature it has to be average of the 7-day maximum pavement design temperature. Okay, and here there are two mistakes. One is air temperature instead of pavement temperature, and the other is they have taken only one value. They have taken it as maximum value. No, it has to be average of 7-day maximum. So next, let us move on to the next option, which is average 7-day maximum pavement design temperature and average 7-day minimum. No, this is correct, but this is wrong, because minimum temperature, it has to be just one value, just the minimum pavement temperature of the place. Okay, maximum pavement design temperature and minimum pavement design temperature, both are pavement temperatures, that is fine, but here it has to be 7-day maximum, average 7-day maximum. Okay, so but this is correct. So the last option, which should obviously be the correct one, average 7-day maximum pavement design temperature and minimum pavement design temperature. So the answer is this. Choose the correct test conditions for rutting in PG. So here, so there's a typo here. Okay, so choose the oscillatory shearing to measure. So what did I say? Let me pick a new slide. For high temperature and intermediate temperature, you are going to test bitumen in a dynamic shear rheometer. The samples are cylindrical samples. And the dimensions of the sample are 25 mm dia and 1 mm height or gap. Okay. So if you see here, these are the two options which could probably correct, but out of these two, which one is the correct value? So we should see what is the criteria also, right? Criteria is G star by sine delta. We will see this why G star by sine delta and G star into sine delta in a few slides. Okay, but for now the G star by sine delta should be minimum of 1 or 2.2 kPa. Okay, here they have not differentiated as 1 or 2.2 kPa. They have simply, so by all the options we can simply assume that they are talking about an RTFO aged sample here. Okay, the only difference in these two options is this, 10 radians per second or 10 hertz. So what is this 10 radians per second or 10 hertz? It is the frequency of loading. Okay, now you saw, so how are these values actually measured? By subjecting the sample to a sinusoidal loading of a particular stress or strain amplitude and by measure and at a particular frequency. Okay, what is this frequency? This one sine waveform. Okay, if if one sine waveform gets over in 1 second, I will call the frequency of the waveform as 1 hertz. If I'm going to finish 10 cycles in 1 second, then my frequency is 10 hertz. So when they say 10 hertz, it means that in 1 second, 10 cycles of this sinusoidal waveform is going to be complete. Okay. This is what should have been the actual value with which the grading should have been given. But by mistake, they did all the calculations with respect to 10 radians per second, and that is why for all the PG grading, we test it at 10 radians per second. So what do you mean by 10 radians per second? Okay. So in one sine waveform, my cycle will complete 2 pi radians. If I'm talking about if I'm talking in terms of radians, right? So if in 1 second, so what is this 2 pi radians? It is 2 into 3.14, which is 6.28 radians. Okay, so if in 1 second, if it completes 10 radians per second, sorry, 10, if in 1 second it completes 10 radians, which means in 1 second it has to complete one cycle and then start the next cycle, because one cycle corresponds to 2 pi radians, right? One complete rotation in a circle is 2 pi radians, right? So one cycle corresponds to 2 pi, one cycle corresponds to 2 pi radians, and in 1 second it has to complete 10 radians. So if it goes in this speed, it means that it is going at it has a frequency of 10 radians per second. Okay, so which means in one cycle would be complete in less than 1 second. Okay, so it is like this. So that is the frequency of loading. That is what we call it as the frequency of loading, and that value for PG grading we always do the testing at 10 radians per second. So the answer to this is C. Okay. So now moving on to the next question, a similar question, but here we are going to talk for fatigue damage. Okay, choose the correct test conditions for the characterization of fatigue damage in performance grading of bitumen. So here, as I told you, the criteria is G star into sine delta. Okay, for fatigue we will see why G star by sine delta and G star into sine delta for rutting and fatigue respectively later. But here it is G star into sine delta, and it has to be a maximum of 6000 kPa as per the new ASTM code. Okay, earlier it was 5000 kPa, and for this fatigue we are going to test the sample at the following dimensions: 8 mm dia and 2 mm height, again at 10 radians per second. We just saw what is 10 radians per second, and I said that all PG grading will be done will be carried out at this particular frequency. Okay, now you should be having a question, why the dimensions of the sample have reduced? Why not use the same dimensions of the sample? We tested the high temperature for high temperature we used a sample of 25 mm dia and 1 mm height, and for intermediate we are using 8 mm dia and 2 mm height. Why not use the same dimensions? Why? Okay, for this let us go back to Galas's lectures, where he said if the material has become stiffer, you should reduce the area of contact of the sample and the plate for many reasons. One is the sample because of the torque limit of the equipment, right? So if the material is going to be very stiff, and if my area of contact is very is large, then the torque required to twist the sample is going to be large, and and there are cases, okay, and there is a possibility that the torque limit of the equipment could be reached, okay. So in that case, you reduce the area of contact of the sample when as you go down the temperature, okay. And also there is something called as compliance, which we will not talk about here, okay. um, the measuring system compliance also comes into play. For that we go in for a different geometry, okay. So yeah, so the answer to this is either one of these two, because these two have 10 radians per second, yeah. And so the only difference between these two options is 5000 and 6000 kPa. This would have been correct had we used an ASTM standard before 2023, okay, before 2023, and this is as per the ASTM standard, as per the latest ASTM standard, okay, which is 6000 kPa. So moving to the next question, here I would like to change the values, because we just now saw the same question. Okay. So if the G star into sine delta is 6000 kPa at 17.5 degrees Celsius, the likely intermediate temperature of Pg is what? So let us see what are the Pg intermediate temperatures in the first place, and where this falls. 16, 19, right? And here this 17.5 is going to fall in between 16 and 19. Okay, so if it falls in between 16 and 19, so, and you are asked to give the Pg grade of bitumen. So what did we see? It should be the next highest temperature after the pass fail temperature. So this is the pass fail temperature or the continuous grade of bitumen. It has to be the next highest temperature after the pass fail temperature. We also saw the reasons for picking the next highest temperature, okay, which is 19 degrees Celsius. Now moving on to the next question. Select the correct option. Rutting and fatigue is expected to occur simultaneously during later part of pavement service life. Rutting and fatigue is expected to occur during early part of pavement service life. Okay. So before we go on through the options, we will see what samples are used to test for rutting and fatigue. What do you do for rutting? You test a RTFO aged sample, which is a short-term aged sample. Fatigue, you test it on a long-term aged sample. So from this itself, you can understand that RTFO is expected in the early stages of the pavement service life. That is why you are not using a PAV aged sample for rutting. So what does PAV aged means? It means that my bitumen has been aged for a longer duration. So it happens fatigue usually happens in the latter part of the pavement service life, where after long-term aging, the bitumen is sufficiently stiff to contribute to fatigue cracking. When you initially lay the pavement, okay, the bitumen is soft, okay, and with time the bitumen ages and becomes stiff. So in the later latter part of the pavement service life, you expect fatigue to be dominant than rutting. Okay, though rutting will also occur, but fatigue will be dominant because the stiffness has increased. In the earlier stages, the bitumen is sufficiently soft, and so you are expecting rutting to happen. That is why you use an RTFO age sample, which is a short-term age sample. So what does short-term aging signify? The mixing and compaction, mixing, storage, compaction, right? Okay, the aging that occurs during this period is the short-term aging of the bitumen. So that is simulated by RTFO aging, and you use a RTFO age sample for rutting because you expect rutting to occur in the early stages of the pavement service life. And fatigue, you use a PAV age sample because a PAV aging is used to simulate the long-term aging, that is the aging that occurs during the service life of bitumen, right? And so fatigue is expected in the later part of the pavement service life. So obviously these two are not the options. Fatigue is expected to occur during earlier part of pavement service life, and rutting is expected to occur during later part of pavement service life. No. Rutting is expected to occur during early part of pavement service life, and fatigue is expected to occur during later part of pavement service life. So this is correct. Okay. Now comes the question which I gave a hint earlier. Given PG, high temperature and low temperature, the intermediate temperature is determined by, right? So as I said, you can measure the high temperature of the place, you can measure the low temperature of the place, but how can you determine the intermediate temperature of the place, as there will be n number of temperatures between this high and low temperatures which are intermediate between high and low temperature, right? So how will you find out the intermediate temperature? Is it the average of the high and low temperature? We don't know. We are going to check now. Okay. So we have been given 4 options, and there is this table which shows you the high temperature of the place, the minimum temperature of the average, minimum temperature of the place, the average 7-day maximum temperature of the place, and the intermediate temperature of the place. Okay. So here you see 3 values, 34 minus 30. Here you see one value which is 46. Okay, 46 is the high temperature of the place, and 3 low temperatures you see, which is minus 34, minus 40 and minus 46. Okay, now for these given temperatures, let us find out which for these 3 low temperatures they have, and this one high temperature, they have given you 3 intermediate temperatures. So let us check which of these options is correct. One option says that it is the average of the two temperatures. Okay, so the high temperature is 46. So let us check for this. High temperature is 46, low temperature is minus 34 by 2. So what is this? 46 minus 34 is 12 by 2, which is 6. Okay, do you see 6 here? This is the value corresponding to minus 34, this is corresponding to minus 40, and this is corresponding to minus 46. Okay, so do you see 6 here? No. So this is not the answer. Let us check the next one, which is H minus L by 2, which is 46 minus of minus 34 by 2, which is, so this is going to be a very high value, which is going to be 80 by 2, 40. Obviously no, because your answer we saw is 10, right? So this is not the option. H plus L by 2 plus 2. We just now saw what H plus L by 2 is. It is 6. 6 plus 2, which is 8. So this is also not the option. And the last option is H plus L by 2 plus 4, which is 6 plus 4 is equals to 10. So this might be the option, but let us check with other grades as well, other temperatures as well. So we checked for the first temperature. Let us check for this temperature, the last one, 40 and 46 and 46. Okay. So H plus L by 2 plus 4, 46 minus 46 by 2 plus 4, 0 plus 4 is equals to 4. Do you see 4 here? I want to check one more temperature, let us say 52 and 34. Okay, and you should be getting 13. Okay, so 52 minus 34 by 2 plus 4, which will be 8 and 1 by 2, which is 9 plus 4 is equals to 13. Okay, so the option is H plus L by 2 plus 4. So once you get the high and low temperature of the place, what you should do is, in order to get the intermediate temperature of the place, you use this formula. Okay. As per ASTM, this is the way to determine the intermediate temperature of the place. Okay. So now moving on to the next question, which is the mixing and compaction temperature test on bitumen is carried out on what? Okay. So mixing and compaction temperature. So mixing and compaction, you do it on an unaged bitumen, original bitumen, unaged bitumen, right? Only after mixing and compaction, the temperature for that the bitumen is subjected to during mixing and compaction is believed to age the bitumen. Okay, increase the stiffness of, increase the viscosity of bitumen, and that is simulated by short-term aging. So mixing and compaction temperature causes short-term aging in bitumen. So in order to find out the mixing and compaction temperature, you cannot use a short-term aged bitumen, because bitumen undergoes short-term aging on mixing and compaction. So to find out the mixing and compaction temperature, you should use an unaged bitumen. Okay. So it is not any of the other options. So this question we already saw. Let us see one more example. Okay. So if the high temperature of the location is 62 degrees Celsius, what is the PG grade? So where does this 62 fall? Okay, it falls in between these two. And what should be the PG grade? This is the PG grade of the, this is the temperature of the location. What did we see? So what grade of bitumen should you ask for now? Should you ask for 58 or 64? If you ask for 58, if your temperature, your binder can only withstand temperatures up to 58 degrees Celsius, but your pavement can be is prone to be subjected to temperatures up to 62 degrees Celsius. So 58 to 62, if the temperature, the pavement temperature falls in between these two, then your sample will fail by, then your pavement will fail by rutting, right? So you should always be on the safer side and pick the higher temperature. Okay, so this is your PG grade, which you should ask for if the high temperature of the location is 62 degrees Celsius. So the answer to this is 64 degrees Celsius. Okay. So now moving on to the next question. If a binder is found to have PG grade of PG 52 minus 16, determine the temperature of the locations in which it can be used to avoid low temperature cracking. Okay. So this is my PG grade, 52 minus 16. Okay. So where can you use to avoid low temperature cracking? What should be the temperature of the place? Should it be less than minus 16 degrees Celsius, which will be minus 17, minus 18, minus 19 and so on, or greater than minus 16 degrees Celsius, which will be minus 15, minus 14 and so on. So what do you think? Here, same as we saw for intermediate temperature, if you pick temperatures less than minus 16 degrees Celsius, then your bitumen is already stiff at this minus 16 degrees Celsius, sufficiently stiff in order to resist the low temperature cracking. Okay, so this bitumen can withstand temperatures only up to minus 16 degrees Celsius. If the temperature of the pavement goes beyond this, then my bitumen will be subjected to low temperature cracking. So your your bitumen should always, this bitumen can withstand temperatures above minus 16 degrees Celsius. Okay, only then you can prevent low temperature cracking. So it should be above minus 16 degrees Celsius. So let us talk about high temperature also while we are at this question. So what temperature, determine the temperature of the locations in which this grade of bitumen can be used. Okay, so this is 52 degrees Celsius. If it is above 52 degrees Celsius, it is 53, 54, 55 and so on. And if it is below 52 degrees Celsius, it is 51, 50, 49 and so on. Now, if you go below, okay, below 52 degrees Celsius, your pavement will be sufficiently stiff, right? So this bitumen can withstand only up to temperatures of 52 degrees Celsius. If you go beyond 52 degrees Celsius, your bitumen will be even more softer, okay, and it is prone to rutting because my bitumen is graded only as 52 degrees Celsius, and so it can withstand temperatures only up to 52 degrees Celsius. So if you see here, it has to be below 52 degrees Celsius. As we saw for high and intermediate temperatures, it has to be the other way around, right? So if you go above 52 degrees Celsius, the bitumen will be very soft and it will be prone to rutting. So it always has to be less than 52 degrees Celsius, only then it will have sufficient stiffness to resist rutting. Okay. The next question, in calculation of the flexural modulus of the prismatic beam, okay, the following parameter is time dependent. Okay, so let us see one by one. We saw that this is the load that is applied on the prismatic beam, a point load at the center, and this load, I told you that it is applied such that it is constant with time. A constant load is applied with time. So this is not the answer. The load applied is not varied as a function of time. It is not time dependent. Are the dimensions of the prismatic beam varied? No, because here you do a non-destructive testing. For a bending beam rheometer, you do a non-destructive testing, whereas the other testing which goes along with this low temperature cracking, PG, you will do a direct tension test where you will subject the specimen to failure, where the dimensions of the bitumen will vary with time, right? So here the dimensions of the prism do not vary with time, so it is not time dependent. Midspan deflection, obviously yes, because so let us see, if the dimensions do not vary, then cross section also does not vary, so this is also not the option. Midspan deflection, we saw, right? We saw the equation for a prismatic beam, elastic beam. Okay, so E is equals to PL cube by 48 deflection into I. Okay, and here this deflection is going to vary as a function of time, because though this equation has been derived from for an elastic beam by using the elastic viscoelastic correspondence principle, we simply substituted the constant value of deflection as a time dependent function. Since this is a time dependent function, the stiffness, the modulus of the bitumen also became a time dependent function. Okay, so the midspan deflection is taken to be varying as a function of time. Okay. So here energy dissipation is used as a criterion for fixing the PG grade for which of the following distresses. Okay. So if you see, we have criteria as G star by sine delta for rutting and G star into sine delta for fatigue. Okay, and here you have criteria such as the modulus at 60 seconds, okay, and the slope of the E of t curve at not 60 degrees, 60 seconds. Okay, so for low temperature, what do? We apply the sample to a constant load with time, measure the modulus as a function of time, okay, something like this. Then at 60 seconds you note down the value of the modulus, and also you note down the slope of this curve, okay. So now this does not have anything to do with energy dissipation, because you're simply plotting the values and getting the values from the curve. But these two criteria, you have no idea, we have no idea how this value has evolved from, okay. So these two values have evolved from the energy dissipation equation, and now we will go and see the theoretical basis for these parameters, okay. So if you see the energy dissipation equation for a viscoelastic material subjected to a sinusoidal loading, okay, be it in stress controlled or strain controlled mode, this is the equation for energy dissipation, and here delta is the phase lag and not as we saw the deflection of the beam or anything like that, because here it is just a sample subjected to torsion, right? Here so this is the this is the amplitude of the strain waveform, and this is the amplitude is this, okay, amplitude of the stress waveform, and this is just pi, okay. So from this equation only we have got the two parameters, G star by sine delta and G star into sine delta. Now this can, so in these equations you do not have the equation, you do not have the term G star, right? You know that G star is the amplitude of stress divided by the amplitude of strain. So now we are simply going to replace stress and strain. For rutting, we are going to replace the value of strain, okay. So now for rutting it is going to be pi G star into sigma dot into sine delta, and that is how we get pi sigma dot square by G star into sine delta. This is for rutting. For fatigue, you are going to replace sigma dot, okay. So ED is equal to pi gamma dot square sine delta. So here rutting, we assume that we are going to use a stress controlled, we assume that for rutting, only if it is a stress control, we control the stress and we measure the deformation, we will be able to get a feel of rutting. So that is why we we assume that the stress is constant, okay. So this entire term becomes a constant, and ED is directly proportional to sine delta by G star. This they have inversed because all of us have a feeling for modulus rather than inverse of modulus, okay. So this becomes G star by sine delta, okay. Similarly for fatigue, okay, we use a stress controlled testing. So if the strain controlled testing, so if the strain is controlled, this term becomes a constant, and so ED is directly proportional to G star into sine delta. So that is how these two parameters have evolved, okay. So these two parameters have evolved from energy dissipation. So the answer to this is both A and B. Now the next question, grade bumping is applicable to what? So let us first understand what grade bumping is, okay. So you know that grade bumping, you actually do the grade bumping when you ask for a PG grade pertaining to a particular location, okay. So let us say my PG, the high temperature of the place is 60 degrees Celsius, and so now what will I ask for the PG grade of bitumen to be? I will ask the contractor to give, I will ask the supplier to give me a PG grade of 64 degrees Celsius. So PG 64 is what I will ask for. Now this is assuming that all the vehicles in that location travel at a speed of 90 kmph, 90 kilometers per hour. Now if the speed of the vehicles in this location is different than 90, okay, especially when it is lower, since my material is viscoelastic, it will be prone to even more rutting. Okay, so that also has to be considered, right? So that instead of bringing a frequency factor or relating the frequency to the relating the speed of the vehicles to the frequency of testing, okay, instead of changing the frequency of testing, what they have actually done is they've applied the notion of time and temperature, like how we relate time to temperature. We saw this time temperature superposition, right? So what they did, if my frequency is reduced, in order to simulate this, in order to take this into account, they will increase the PG grade by 1. Okay, so instead of asking for 64, the contractor or you will ask for a PG of grade 70, because my vehicles are going to move even slower, thereby making the bitumen to be more prone to rutting. Okay, so this is called as grade bumping. So instead of directly changing the frequency of testing, okay, depending on the speed of the vehicles, what they actually do is they will ask for a even stiffer bitumen, because since slower speed vehicles are prone cause the bitumen to more rutting. Okay, they are assuming that if I bring a even stiffer grade of bitumen, then I can take care of this. So that is why they, instead of asking for a PG grade of 64, you will ask for a PG grade of 70 if the speed of the vehicles is lesser, say around 40 kmph. Now so this is when the vehicle is moving slower. What will happen if the vehicle is at a stop, is stationary? There you will again do a grade bumping. So if it is at a stop, you will do a grade bumping of 2 grades, and if it is moving slower, you will do a grade bumping of 1 grade. So this is done only for high temperatures, not for low temperatures or not for intermediate temperatures. Okay, so grade bumping is applicable to high temperatures. Okay, now moving to the next question. The test temperature chosen for PAV aging of the bitumen depends on what? So this is pertaining to the aging simulation. Okay, we saw two kinds of aging, right? RTFO aging and PAV aging, to simulate the aging that happens in the field. Okay, so this RTFO aging is done at 163 degrees Celsius for 85 minutes, and this PAV aging is done at 3 temperatures: 90, 100, 110 degrees Celsius. This also has an airflow, okay, for 2.1 megapascal with 2.1 MPa pressure, and one more thing, time for 20 hours. Okay, so this temperature is what they are asking. So what temperature will you pick for doing the PV aging of the bitumen? And we saw that it will depend on the temperature of the place. Okay, not the number of years or the temperature susceptibility. None of these options. So if my temperature is cold, if the temperature of the place is cold, I am going to age the bitumen at 90 degrees Celsius. If it is mild, if it is mild, it is 90 degrees Celsius. If it is moderate, it is 100 degrees Celsius, and if it is high, it is 110 degrees Celsius. So it is going to depend on the climatic location of the place. Now, the next question: which of the following statements is correct? So let us go one by one. Higher the dynamic modulus, higher will be the fatigue life. What did we see the criteria for fatigue life? G star into sine delta is maximum, it should be 6000 kPa. What will happen? If it goes more than this, then it will be more stiff, then the bitumen will be subjected to fatigue. Okay, so if the bitumen is stiffer, then it is prone to fatigue cracking. So if it is stiffer, when will it be stiffer? If the modulus is high, the material will be stiffer. So if it is stiffer, if the modulus is high, it will be the fatigue cracking will be more, fatigue damage will be more, and so the fatigue life will be less. So this is not the option. Okay, lower the value of phase angle, higher will be the rutting life. So what is the criteria for rutting? G star by sine delta should be minimum of 1 kPa. So here they are not talking about modulus, they are talking about phase angle. What will happen if this value is low? If this sine delta is low, if this delta is low, then G star by sine delta value will be more. If it is more, then the material will be stiff, and so it can resist rutting. So it will have a higher rutting life, right? Because it has to be minimum of 1 kPa. If this phase angle is more, then it will be stiffer, and so it will have, if this phase angle is lesser, then it will have more than 1 kPa, it will have a higher stiffness, and so the rutting life will be higher. Also, you can relate it to something like this. This can vary between 0 and 90 degrees, right? This delta. 0 is for elastic materials where it is very stiff, and 90 is for viscous materials where it is fluid-like, right? So if it is fluid-like, if the phase angle is more, then it has more fluid-like properties, and so it can easily flow and rutting will be more, right? So at lower values of phase angle, this it can resist rutting more, and so the rutting life will be better. Okay, higher the dynamic modulus, lower the fatigue life. Okay, we will use the same term expression, G star by sine delta. So if the value of G star is more, then this criteria will be higher. Okay, this can be more than 1 kPa, this will be more. So if the modulus is more, obviously the material is stiff, right? And that is what you want for rutting. So higher the dynamic modulus, higher will be the fatigue life, better will be the fatigue life. So this is also not the option. Okay, so the answer to this is the second one. Criteria for low temperature grading of binder is what? Okay, so what did we say? For a bending beam rheometer, we subject it to a constant load with time and measure measure the deflection delta of t. Okay, and from delta of t we will get E of t and plot it as a function of time. Okay, now you will measure this deflection at certain time intervals. Okay, and you will take the value corresponding to 60 seconds. Okay, now if you know, sir would have mentioned that if your temperature of the place is minus say 20 degrees Celsius, you will do the testing at a temperature 10 degrees more than this value. Okay, so you will do it at minus 10 degrees Celsius. So you will pick a value 10 degrees more than the lowest temperature of the place and test the bitumen at that temperature. Find out the values at 60 seconds. Okay, there is something relating this 60 seconds with this 10 degrees Celsius. Okay, so earlier they saw that if they had to do it at the exact temperature of the place, then they would have to extend the duration of the testing. Okay, and then measure the value at an extended duration. In order to reduce the temperature test timing, they increase the temperature. So this is using the time temperature superposition principle. Okay. So here you should ensure that the material response is linear, right, as sir said. So if it is linear, you can apply the time temperature superposition principle. That is why they are increasing the temperature by 10 degrees Celsius and measuring the value at 60 seconds. Okay. Had they wanted to test it at the exact temperature, then they would have to carry out the experiment for a longer duration. Okay. So now they will measure two values. One is creep stiffness, which is E of t, E at 60 seconds, and you will fit a curve to this E and find out the slope at this 60 seconds, which they will call it as M at 60 seconds. Now we understood why G star by sine delta has to be minimum and G star into sine delta has to be maximum, right? Now here also they say that this stiffness has to be maximum and this M slope has to be minimum. Why are they saying this? Let us see. Okay, one second. Okay, yeah. So low temperature cracking and fatigue cracking are kind of similar, except the temperature, and low temperature cracking also has the influence of temperature and the number of repetitions of load, whereas fatigue also only has an repetition. Okay. Now, so what did you do for fatigue cracking? You gave a maximum value, right? Maximum 6000 kPa. So if it goes more than this, it is prone to fatigue cracking. So as I said, low temperature cracking and fatigue cracking are more or less similar. So here also the stiffness, here also you are limiting the stiffness. And so for for low temperature also you should limit the stiffness. Okay, so here also the stiffness, which is the creep stiffness here. Okay, so here it has to be, since you are applying an oscillatory loading, you are measuring the stiffness in terms of G star and sine delta. So G star into G star and sine delta. Here, since you are subjecting the bitumen to a constant loading, which is a creep load, you are measuring the creep stiffness, and this creep stiffness you are limiting it to 300 MPa. Right? So if it is more than this, then the material will undergo low temperature cracking. Okay. And also they are using one more value, which is the slope. And they say that this slope has to be minimum value they are giving. Why do you think there is a need to mention the slope, and why do you think they have given a minimum criteria for it? There are there's only one reason. Okay, one is we will think that if the stiffness is varying very slowly, then it is better, right? But you should understand that this is for a constant load. This is not like I'm repeating the experiment for a number of cycles and I'm observing how the stiffness is decreasing. That time we will want the stiffness to vary very slowly, because it means that if the stiffness is varying very fast, then the material is damaging, right? But here I'm subjecting the material to a constant load, and when I subject it to a constant load, we saw that if the material is elastic, then the deflection will be the same, and if the material is fluid like, okay, there will be a momentary deflection and it will immediately relax. And when it is a viscoelastic material, it will Sorry, one second. No. Sorry. We will go again. Here we are subjecting it to a constant load, right? Okay. So here we are subjecting to a constant load, and here the deflection for an elastic material will be constant, and for a viscous material it will increase like this, right? And for a viscoelastic material it is going to be a combination of these two. Now they are limiting the slope of this equation. Okay, it has to have a minimum value. Okay, which means the slope can be as higher as possible but not below this minimum value of 0.3. Okay, so that is what they are limiting in a low temperature grading. Okay, so maximum value of creep stiffness is 300 and minimum value is, or minimum value of the slope of the response is 0.3. Okay, now moving on to the next question. As per ASTM D6723, the brittle ductile is what? So sir would have explained three kinds of failures. One is a brittle failure where the stress strain relationship is linear and after that it will rupture. Okay, a ductile failure where there will be a gradual change, so there will not be any sudden rupture, but there will be a long deformation before the material fails. That is considered as the failure. The elongated shape of the elongated deflection is the ductile failure. Okay, and there's something called as brittle ductile failure where the stress strain is curvilinear. Okay, curvilinear. Okay, and there will be a sudden rupture. Okay, so the answer to this is a type of failure where the stress strain curve is curvilinear and the ductile is, and the failure is by sudden rupture. Okay, so now there are questions remaining corresponding to the modifiers. Okay, since the next week also there will be a few more lectures on modifiers, I think it will be better if we answer all the questions related to modifiers in the next week. So we will do that in the next week. So this week's session is over. Thank you so much.